Oli, eu deixo essa tela ou eu tiro ela?
Pode deixar agora.
Tá.
A gente vai fazer. We will start the YouTube streaming now.
Oli, eu deixo essa tela ou eu tiro ela?
Deixa ela, gente. Pode deixar. A gente vai fazer. We will start the YouTube streaming now. Deixa ela, gente. There is a delay with my speak.
Oli, it's normal on to be transmission.
Yes?
Yes.
Okay.
It's
Okay.
quite normal.
There is a delay with my speak. Okay. Pronto. Okay. It's more people entering. Okay, Katarina, I can start? Yes.
For me, yes.
Yes. Okay. Hello. Good morning, good afternoon, and good evening. My name is Oli, and I'm the chair of the workshop Chemical Abundance in Gaseous Nebulae from the Milky Way to the early universe. The main reason for us to decide organizing this workshop is because we have noted the lack of an event about this specific subject, which in general are measured among other subjects. So I believe that the benefit is to bring updated information for everybody, and also to have the opportunity to invite well-known professionals from many specific areas. I also believe that we will have a great opportunity to provide you the most recent developments in the field of science. It's a great moment for us to produce a more solid networking between several professors and the students who are attending the workshop. Finally, I believe that this workshop will help to develop the astronomy in Brazil and up to an international scenario. Please make sure that you keep your microphone closed during the entire presentation. You are free to send any questions to us using the Slack platform. It's important to remind that we have a code of conduct, so it's important for us to be respectful with each other during the entire workshop. We are very happy to inform that we have over 200 participants from over 2 countries in total. This workshop is supported by the Universidade do Vale do Paraíba, Univap, Institute of Research of Development of Univap, IPND, Associação Argentina de Astronomia, GMT Brazil Office, and the Instituto Nazionale di Astrofisica, Italy. Now, in order to give the welcome on behalf of the Univap, I would like to invite the research director, Mr. Leandro Reneiro, and the director of the IPD, Ms. Lúcia Vieira. After Catarina Aidar will give we will speak some few words about the Slack. So it's all. Thank you very much to attend this workshop.
Thank you, Oli. It's my pleasure to welcome all the participants today for the 5 days workshop. I'd like to thank you to coming and join us in this digital platform with the social distance norm due to the pandemic situation. Um, it's for me, it's a great honor to be part of the open ceremony, and I hope you enjoy and you have a great event and many scientific collaboration. And I also would like to thank the organizing committee for the enormous efforts behind the workshop, and also all the participants that is going to present the work in the conference. Thank you very much. Have a good time. Thank you, Lee.
Welcome. And Lucia, I think you
Okay.
can.
On behalf of Univap, I would like to welcome all participants of the third workshop, Chemical Balances in Gaseous Nebulae, from the Milky Way to the early universe. Please enjoy your time at the workshop, share experience, and proliferate acknowledgement. Thank you, and have a very good time at this workshop. Thank you so much, and have a good time.
Thank you, Lucia. Now I think Katarina can speak some orientations about the Slack use.
Hello, everyone, and welcome to our workshop. My name is Katarina, and I am here talking on behalf of the LOC, the Local Organizing Committee. So if you have any issues, whether they are technical or any other issues, you can find me to help you out. And I'm going to tell you how we're going to make the questions in this online format. So here on Zoom, we have two options of making the questions for the participants that will be giving the talks. We can write the question in the chat, or we can raise our hand. We click on participants, and then there is an option of raising the hand. So if the chair of each section will direct the questions that will be made during our moment here on Zoom. And if there is no time to answer a few of the questions, then we can go to Slack and continue the discussions there. So we have created a channel for each day in case you have specific questions about the talks. And in case you have more wide questions about the subjects of the talks, we also have divided, for example, H2 regions, planetary nebula, AGN, high redshift, and so on, in case you want to ask something that is not specific to one of the talkers or related to one of the talks. Moreover, I think that we can use Slack also for any other kind of exchange of ideas, because once we don't have our coffee breaks at live, so we can use that space in order to talk to other participants and to do our network on the best way that we can. So I think for now, that's it. Thank you very much. Welcome and enjoy.
I think we have used the not the total time to the welcome, and you have time to speak something. I think I can speak some more words. Have time, and this is the third workshop. And the first one happened at 2016, and we have about 50 participants from about 80 countries. And the second workshop happened at 2 days ago, and it was in honor to Manuel Peberti and Roberto and Rafael Costeiro. They are the pioneer in the study of chemical abundance in gaseous nebulae. For this reason, we did this workshop in honor to the these researchers. Also, we did some we unfortunately in this 2 days before the workshop, Michael Dopita passed away, and he was invited of this workshop. So this workshop now is also in honor to Michael Dopita as well. He was one of the first researcher, one of the most important research in this area of chemical abundance. So this workshop is also in honor to Michael Dopita. Okay, and to it is here with us Antonio Peberti, is the son of Manuel Peberti and Silva Torres Peberti, and we will tell us also of the part of the Manuel Peberti studies. So I think we will have a good value workshop, despite of this new format of this workshop. This how, as Katarina told, there is not so good meet in person the people, but this kind of workshop has permitted the people from very different countries to be access to workshop. For example, from these 200 participants, you have participants from Nepal, for example. For these participants, probably it was very difficult to attend the workshop in Brazil. And my idea is continue with this workshop. It will happen each 2 or 3 days, depending on the available of the organizer and the if he is really necessary. I don't know if the next workshop will be in this format or not, but I'm sure this workshop is a sort of workshop, and it will happen certainly. And in my opinion, this workshop is my principal contribution to the study of gaseous nebula, despite of I published some papers in this area. This is not important comparing to the possibility to provide this workshop. Okay, I'm very happy we are there. It's an honor for me. Permitted to access to many students, to be contacted with very important professor in the area like Gary Fallon, Cesar Esteban, and the other ones. And I think it's all. Thank you very much to attend. I think it's difficult because of the different time zone, but we can not fit that. Okay. Okay, we have more 60 minutes. If someone wants to speak some words, it's free. Or we white.
Hello,
Hello, Angelis.
I'm Ángeles Díaz and from the Universidad Autónoma de Madrid. And I just want to express explicitly my thanks to the organization of this meeting. I'm very sorry to have missed the other two events because I couldn't travel. But now that we have other means of meeting, I want to thank this effort, and I'm very happy to be here to share our work, to meet friends, even virtually. But I think that's more than enough. I'll give you some image, if I can, of myself, so you can see.
Okay, I can see you now.
Just I will keep it
Yes.
for the rest of the meeting because we don't have such wideness of band to to have this open. But thank you very much to all of you for the organization of this meeting.
Welcome, Angelis. I think it's the first workshop you attend.
Yes.
Yeah, okay.
Yes.
Well, for a few words. Since the first workshop, my concern is to provide a very cheap workshop in order to the students have access to the workshop, because in my opinion, most part of the workshops happen in very expensive hotel, very expensive places. So I think why not to do a very cheap workshop, and for still reason, um, I I always have this concern to providing a workshop with a low cost, and this will be my idea ever. And I think this is working because we are receiving people from different countries, and the cost of the workshop, of course, there is a cost, but it is not transferred to the participants, at least in this workshop.
Hi, Ali. I just wanted to quickly say thank you to you and all the other organizers. I was very lucky to be able to come to the first one of these in Brazil, and it was really wonderful to make so many connections with so many scientists around the world. And it really did, for me, foster new collaborations, and was even where I met Carla Ariana Cordova, who is now my postdoc. So it's been really fantastic, and I'm excited to meet so many new faces again this week and look forward to the science we can do together in the future. So this has been really excited to see this still going, and thank you for all the work that you are all putting in to make it happen.
Thank you, Daniele.
So while we wait a little bit, let me just give you some information about the poster section. though we will not have a poster section today, they will start tomorrow. And then I kindly asked the poster presenters that did not send us a slide that you want to present, please do it so quickly. And we will have a more or less 1 minute presentation of each of the posters. And then you can see the posters in more detail and ask the questions you want on the channel of posters on our Slack workspace. So I think that the posters are a good opportunity for sorry, this kind of network that Danielle just mentioned. So it's important for us to support the works and to give some feedback to the students. That will be very nice of you. Not only students, some of the professors are presenting posters as well instead of talks. So I hope we can make these discussions go further than simply watching the talks, but also talking to people and interacting.
Okay, Catarina, a guy is asked to you post the Slack info again, please.
Okay, I'll do so. Okay, thanks.
Okay.
Hi everyone. So I'm posting on Slack now the link to join. I think that it has been posted by Francisco Belfiore as well. And in case you cannot access it, you can look for our hashtag is, let me share the screen here and you will also see. Our hashtag is ChemaGas 2021. And then if you look for that in the Slack workspaces, you can also find us there. And in other cases, we have sent you, I think last week, a file with some instructions on how to use Slack for those that are not very used to this tool. So there you can find these links to access our workspace, and also some tips of how to use it for those who are not, who haven't been using Slack recently in this pandemic times. So if you need for those who need a version in Portuguese, we can also send it. It's done already. So you can just email us and we will put it forward. But yes, thank you, Alejandro. I think that when I put the link, there's a part of the link that is not being inserted. Yes, there is a space, but he has sent the correct version now. So let me do this again. And the hashtag ChemGas 2021. Thank you.
Catarina, do you see Roberto Maiolino here?
Yes, I'm
oh,
here.
yes. Okay, thank you.
Hello.
I was looking for you, but there are many people. Okay. Thank you, Roberto, to help us with the workshop. It's an honor to have you here.
So I'm chairing the first session, and but I guess we still wait a few minutes, I understand.
Yes.
Uh,
I think you are co-roasted or not yet,
I'm not sure.
because I'm looking for your name. Find Roberto. If not, I do that.
I
Oh,
don't,
here.
I don't think I'm ghost.
I'm not the roasted. I don't know why.
It says that Antonio Pembers is the host, but I don't know
Uh,
how that
uh,
happened.
I changed it so.
Antonio, can you set the host for Oli, or at least put
Sure.
Roberto as the co-host, please?
Because I type wrong. Okay, thank you, Antonio.
You're welcome.
Now I'm the roast again. But I cannot see the participants. I don't know why. What about okay. Yes. Okay.
So maybe Gary can start sharing his presentation. Gary?
He was here.
Yeah.
Okay, here. Yes.
Okay.
There.
Hi.
Hello, Gary. So maybe I start introduce the session. Yeah. Let's, hello, Gary. So I'm glad to chair this first session of the workshop, and the technicality and logistics have already been described by Katarina and Oli. Just a reminder that at the end of each presentation, if you want to ask questions, you use the raise hand option on the bottom of your Zoom screen, or you can type Q in the chat if you want. And Slack is mostly for questions that we do not have time to answer during the Q&A, or that you simply want to ask afterwards. But feel free to use Slack as well anyhow. So Gary, I will. So we start with Gary Ferland, which will give a review on the measuring the chemical abundances in nebulae. And I will switch off my camera. I will switch it on again 5 minutes to the end to try to warn you. So keep an eye on my camera. Okay. Thank you. Please, if you're ready, you can start.
Okay, well, thank you very much for the invitation. It's wonderful to see everyone virtually. But I want to talk about today, I was asked to review abundances. That's not really something I'm working on an awful lot, something I'm knowledgeable about. My basic interests have long been the physics of the plasma itself, trying to understand how the gas works, what it's doing. This all began ages and ages ago when Martin Rees hired me as a postdoc at Cambridge. I had an office next to Martin for 2 years. Mike Seaton was just a 90-minute train ride away in London. Alan Burgess was the city center at Damptic. So it was a wonderful place to be working on this kind of physics. And I was trying to work on the hardest problem, which is very, very dense gas, very close to a black hole and an accretion disk. And so if you can do that problem, the low density problem comes along automatically. And so it can consist of developing a computer program, a software plasma simulation code, which was in fact named after the weather in Cambridge. It's called cloudy, because all the good names by that time had been taken. So when I talk about my perspective on this problem from that background, and just another aside, Aristotle identified two difficulties, two complexities in trying to do things. There's the accidental complexity, and then there's the essential complexity. The accidental complexity was working with computers long ago, was very challenging. The atomic data was in bad shape back then, much better shape now. Observations were hard to obtain, hard to calibrate. So there's a lot of things that we can do something about. They're accidental difficulties. They slow you down. They get in your way, but they're something we can cope with. And then there's the essential difficulty. The essential difficulty is the real art, what we're really after. And to measure the abundances in mission line objects, what you've got to pin down is the temperature, the gas temperatures. That's what I want to talk about today. So this is a context, this beautiful periodic table by Jennifer Johnson. This has been on Astronomy Picture of the Day off and on several times. It shows the different places where the elements are produced. So this is where we have to deal with. This is what's called the gas cooling function. And so this is a plot showing the gas temperature. So when I say temperature in this plot, mainly it's going to be the gas temperature. And what this shows is the rate that thermal energy in the gas is converted into light that escapes. So it's cooling. The thing that is critical in this is the gas does have a temperature, sometimes called the electron temperature, or more generally called the kinetic temperature. There is a kinetic temperature, the temperature that corresponds to the heat in the gas, and the gas is cooling off. And the cooling is by collisional processes in the gas, which change kinetic energy of motion of the electrons into light that escapes. And so this cooling function has this very characteristic shape. This is very classical, goes back to very important papers in the 1960s. This is a lot of atomic physics, but there's a 1, 2, 3, 4, 5 order of magnitude range in how rapidly the gas cools depending on how hot it is. I want to talk about different things here. The way the temperature in a nebula works is something produces a heating rate. This blue line represents some imaginary heating rate. Maybe it's shocks, perhaps as photoionization did to a star, but something is heating the gas up. So we're imagining a nebula out there in space, and something is heating up the gas with this particular rate. So it's 2 times 10 to the minus 23 ergs per cubic centimeter per second. What temperature does that gas equilibrate at? And so the equilibrium temperature is going to be where this heating, the process giving energy to the gas, making it hotter, is equal to the rate that the gas cools off. And there's 3 places where these 2 rates are equal. There's this place, and this place. Next thing you have to worry about is whether or not that solution is stable. And the way you do that is you do a little Gedanken experiment where you imagine that the gas is right here in equilibrium, and if you make it too hot, move it over here. What happens if you've made it too hot? What's happened is it's cooling much more quickly than it's heating. So that means it's going to overcool and it'll cool back down. So if you disturb it either way, it will go right back to where it started. So that's a stable equilibrium. This is also stable. Anything with a positive slope is stable. This is unstable. If you have a parcel of gas right here, and if you were to make it a little bit cooler, what's now happened is that the cooling has gone up. And so it's going to cool off very quickly. And what will happen is it'll shoot over to this phase. So you'll find gas here, you can find gas here, and you can find here. So these are the stable phases that you can find with this cooling function. What you're actually looking at is the many-body Schrodinger equation. So this is a change of electron configuration. These are change of electron terms, and these are change of electron levels in ions. So it's a beautiful thing. If you start out from the many-body Schrodinger equation, you get up to this, which is the structure of an H2 region. I'll come back and see why this is. So an idealized structure of an H2 region is something like this. So we have the star cluster in the center. So the star cluster has lots of young stars. The young stars are born from molecular clouds. They're short-lived, so they always lie close to a molecular cloud. The young stars are extremely windy. They're short-lived and windy. There's a lot of winds coming off from the stars, and the mechanical energy due to the winds will shock the surrounding gas. You have mechanical energy input, and that creates this very hot bubble. So that is populating this branch of the cooling function right here. This is not a lot of energy in this phase. It does not. Most of the light energy coming out of the stars is actually in photons. So there's a huge cavity. We'll see some images in a second, and taken with optical light, it looks like there's nothing here because X-ray light doesn't emit much. So then the next layer is the gas goes over to the warm phase. This is what we would call the optical H2 region. So when it goes over here, you see that this is the last stable phase, and then it jumps over to this 10,000 degree phase. So that's what we call, you look at the Orion Nebula, that's what we're looking at, is this phase of interstellar medium. And then as you go deeper and deeper, the radiation is attenuated and it jumps phases going down to an H0 region or PDR and the cool region or the molecular cloud. So if we go back here, so we have the hot bubble in this phase. The H2 region itself is largely this gas phase that jumps from here to here. And then if it cools off at the hydrogen ionization front, it jumps phases again down to this phase, the PDR and molecular cloud. So this is what you see out there in the sky. Now that's all very theoretical 1D sphere. So this is Thordy Doradus. This is the closest starburst to the Earth. I believe it's the biggest starburst in the local group. So it's down in the clouds. So what you see is a star cluster in the very center, and then the nebula around it looks like it's like Swiss cheese. It's got these great big holes. Looks like Swiss cheese until you point an X-ray telescope at it and combine the X-ray image with the infrared image. So Lisa Townsley has done that. The blue light is the X-ray imaging. So you're looking at the hot phase, the very hot gas is filling in the holes in the Swiss cheese, and then the orange is showing, I believe, a Spitzer image of dust emission, which is tracing the cooler gas. This geometry is found many, many places. This is a famous image Yu did of the Saturn planetary nebula. So on the left, we see the Space Telescope image. Again, it's the Swiss cheese kind of affair with some empty holes in the nebula. And then if you add in the X-ray, the hot gas emission, you see that the X-ray hot bubble is filling in these voids. If you work the numbers here, what you find is that the pressures in these regions are about the same. So this very definitely hot gas pressure in the blue representing the X-ray emitting gas. So that's not a strong statement. Gas pressure being the same. There's uncertainty, substantial uncertainties in the estimates of all these, but this consistent with this being basically in pressure equilibrium. In the case of a H2 region, when you get to the molecular cloud, the magnetic field turbulence is another source of pressure, but it does work out that these are in something like pressure equilibrium. So this is what we're working with when we look at a nebula. I know of no exceptions in the galaxy where you can look at an H2 region and actually see what's going on. What it is a hot young star very close to the molecular cloud that birthed it, producing ionizing radiation, and then the ionizing radiation striking the cloud. So this is a piece of the very famous Space Telescope image of Pillars of Creation, or M16. So here's it's kind of a thimble of ionized gas around a finger of neutral, very cold, dusty molecular gas. So this is a molecular cloud. There's stars. The actual star that's doing this is far off to the upper left on this image. The starlight is striking the molecular cloud, creating an ionized layer on its surface. So the H2 region that makes the visible light that we see is a surface phenomenon on the surface of the molecular cloud. I know of no exceptions in the galaxy where you can look carefully and see what's really going on. This is a face-on view of the same geometry. We're looking at this edge-on. So if you were to be over here looking down at this, you would see this is the Orion Nebula. There's a large molecular cloud called OMC1 that's on the other side of the nebula. Here's the ionized layer, and then here's the trapezium star cluster, which produces ionized layer. So this is what we're working with. We're working with a thin ionized layer on the surface of a molecular cloud, trying to understand what's going on. In the case of the H2 regions in the planetary nebulae, it's a bit more complicated. A lot of things are happening in a planetary, but there is a molecular region and an ionized region which is adjacent. So the problem we've met here in Brazil to work on is to understand how to get the abundances out of the spectrum. So this is the Orion Nebula, and here on the left side is a spectrum. It's taken from the Osterbach textbook, and it shows what you can work with in the spectrum. Well, if it's a low redshift, if it's in the nearby universe, we can work with a region from about here to here. And if you go out to higher redshift, then you get down into this region as well. unfortunately, the interstellar medium becomes opaque at wavelengths down around here, so it's very challenging to see anything down there. So what you're looking at is a lot of very strong lines. These are hydrogen recombination lines. The physics of that has been well known since the work of Menzel and Baker in the 1930s. Then these are the O3 forbidden lines, which are the strongest lines in the nebula. So this is hydrogen, hydrogen. That's no surprise. That's most of the atoms. Helium is the second most abundant element. It is making some weak lines, this guy here. And then the third most abundant element in the solar system is oxygen. So that's producing these strong lines, this strong line right here. So what I'm going to do is look at a homework problem. I've been organizing a series of cloudy workshops every year or two in various places. So there's this plasma simulation code called Cloudy that I've been working on for some time, and we have workshops, something like this workshop here, but a week long, just on that one code. This is one of the homework problems we work on in that workshop. I'll post the input script for Cloudy for doing this if you're interested. What this shows is the metallicity, capital Z, capital Z, and the sun would be right here. So the solar metallicity on the scale is a 0. This would be 10 times solar, 3 times solar. So down here is a 10th of solar. So mostly we're thinking about abundances in this range from solar, maybe a couple times solar down to a 10th of solar, something like that. And then this is there's less to this than meets the eye. This is just showing the oxygen to hydrogen ratio as a function of metallicity. So if you take, on this scale, solar is 0. And if you were to go up here, what if I did this right, this should be the abundance of oxygen in the sun. And so if you do something very simple and naive, if you assume that the gas temperature doesn't change, if you assume that the gas and the temperature in the issue region does not change, this is what you would predict for the O3 forbidden lines relative to H beta. So these are 2 strong lines in a very easy to work with part of the spectrum. It's in the visible, the green is in the green part of the spectrum. And so detectors are extremely efficient there. And there's data in this part of the spectrum going back a good part of the century. So there's been a lot of work done in this part of the spectrum. So if you think about this line ratio, if you do not solve for the temperature, the O3 to H beta ratio would go up linearly up and down. So if you look at this, this is a source of some optimism. If you look at this plot, it should be really easy. There's no essential difficulty here. That should be very easy to measure the abundances accurately. That's not what happens though if you conserve energy. So if you turn on Cloudy's, all the solvers in Cloudy, this is what you'll find. So it's paradoxical. This is solar to a 10th of solar. Actually, at solar, the O3 to H beta ratio is here. At a 10th of solar, it's here. To the precision of the pointer here on Zoom, the O3 to H beta ratio has not changed at all. So this is I would assert, is what really does happen in nature. So there's for the region of interest in much of astronomy, the O3 H beta ratio is pretty constant. It doesn't really depend on the oxygen to hydrogen ratio. What's happening here is what's called the thermostat effect, and this is the essential difficulty in nebulae, is you need to be able to understand the temperature of the gas. The thermostat effect represents the fact the energy is conserved, so the heating going into the gas, that's in the H2 region, that's starlight. The heating going into the gas the energy source is starlight, that's equal to the cooling, and that's going to be the sum of these forbidden lines. These forbidden lines are how the gas cools off. So an electron, a free electron, hits an O++, causes an internal excitation that produces an emission line. So the thermal energy has been converted into light that escapes. That's cooling. And so the cooling is set by the heating, not by the number of oxygens. And so the effect is when you raise the oxygen abundance, which we're doing as we go from here to here, as you raise the oxygen abundance, there's more and more oxygen present. So it's much easier for the gas to cool off. The oxygen intensity doesn't change. What changes is the gas temperature. It cools down. So it's like a thermostat in a room, keeping things about the same. So another way to think of this is, so here's our H2 region, M16. This is the glowing layer. Probably much of the light we're looking at is the O3 line. And so the total brightness of this layer doesn't depend on the oxygen abundance. It depends on the starlight that hit it. So the ionized layer just emits a large fraction of the incident light, no matter how much oxygen is in it. So this is a lot of words thrown here on a slide. So the strong forbidden lines are the main cooling. Their intensity is set by the heating, the star, rather than the abundance. This is officially another Cambridge tie-in. This was the Stoy method of measuring stellar temperature. So early in the 1930s, the best brains on the planet were fascinated on how this plasma works. And Eddington had a student named Stoy who did a thesis on understanding the thermal equilibrium of nebulae. Stoy pointed out that the O3 to H beta ratio actually measures the stellar temperature, not the oxygen abundance. It's the Stoy method of determining stellar temperature. Unfortunately, he had a short career. He went to California, worked for a bit on astronomy, came back to the UK during World War II, went into defense work, and never came back to do research in astronomy, but he had a very illustrious beginning. So this can be called the Stoy method of determining stellar temperature. It's seldom used for that now. Instead, it's the essential difficulty in understanding these nebulae. So then you get into the question, you got to measure this temperature. Does the temperature exist? Do you look at a nebula like this, and obviously very strong density in homogeneities? Is there a one temperature? Manuel Pembert long ago proposed that just as the density is fluctuating, the temperature should also be fluctuating, sort of maybe in lockstep somehow. So there's this very important paper which is unsolved today. So it has 600 plus citations. It has to be one of the more cited observational papers on this. So what he said is that perhaps it would not be a temperature, but rather there's a range of temperatures. It's fluctuating. It's called temperature fluctuations. So it's also called T squared. Temperature and homogeneities. Temperature fluctuations are the usual word, T squared. And so the idea is there were density fluctuations, perhaps the temperature is fluctuating. And the basic problem here from the theoretical side is that the cooling function in the region we're working with, 10,000 degrees, is very rapidly increasing function of temperature. So if you were to imagine the temperature fluctuating back and forth a little bit, the cooling would go up and down by orders of magnitude. And so with theoretically, these fluctuations should be very, very, very small. So that's been the prediction, basically from the time that Manuel had the courage to first predict this. So observe this rather. So observationally, it's a challenging measurement because it involves measuring the intensities of very faint lines in the spectrum. So you need a big telescope, and you need to be very careful So I would count this temperature fluctuations as being the biggest unsolved puzzle in nebular astrophysics. So that this challenges the essential question: is there a temperature at all, or is it fluctuating? A second thing came up 80 years ago and was settled in the late 40s across the 1950s, but has recently made a resurgence, is the idea that perhaps the electron distribution is not really Maxwellian. So this is a plot showing a Maxwell-Boltzmann velocity distribution here. And this is, if there's one temperature that defines the ionized gas, it would be this, the gas would lie along this curve here. So this is the velocity, say, of the electrons in the gas. So that if it's along this curve, it's exactly one temperature. The kappa distribution was originally introduced when you find plasmas with very, very different properties strongly interacting with one another. And the kappa distribution has different properties than the Maxwellian. It can affect temperature indicators. It's known that if you have very, very different plasmas, probably the best case, the closest to home, is the solar wind interacting with the top of the Earth's atmosphere. So you have million-degree gas, very highly ionized, hitting the atmosphere of a terrestrial planet, us, and it's cold and molecular. And so there's an interaction layer where you have the really crazy situation. The super hot gas, very cold gas with very different properties interacting one with the other. And so you do get non-thermal distribution. The kappa distribution is a non-thermal electron distribution. There are other examples as well. There's parts of the sun's outer surface that do this, and magnetic fusion, tokamaks. And you can find regions and diverters where this is important. This is so important that it was really looked at really hard by some smart people. David Bohm and Larry Auer wrote a paper as slightly indecipherable in the APJ in 1947. Lyman Spitzer knew this was a very fundamental problem, and he wrote a large number of papers and books on this subject. And so what the upshot of this work was that electrons should be very overwhelmingly Maxwellian. The reason is really, really simple. In an ionized gas, the fastest particle is the free electron. The mass of a particle is the inverse square root of the velocity of a particle in an ionized gas is happen to be squared as kT, so it depends on the square root of the mass. The fastest particles are the electrons. The most frequent collision in an ionized gas are two electrons hitting each other because they're really moving around, they're charged up. So electron-electron collision, if you read this last chapter in Jackson, that's a homonuclear collision. There's no dipole moment, so it doesn't make any light. That's a perfectly elastic collision. So the point here is that the fastest collisional process in an ionized gas is electron-electron collision. That's an elastic collision. That's what you need to set up a Maxwellian. And so what they found half a century ago was that by many orders of magnitude, the electrons will be Maxwellian. So there's been two fairly recent papers. The first one was a Revista Americana paper, in which we basically outlined the original Spitzer arguments for why the electrons will be Maxwellian. And so Spitzer proposed several tests, and we conducted these tests for nebulae, and you find it's not close. By 8 or 10 orders of magnitude, the electrons will be Maxwellian. Drain, with a student, did a numerical calculation following a high energy electron being injected into a plasma, and basically basically got the same Spitzer result, that the electrons are very closely Maxwellian. So where are we here? The T-squared problem, the temperature fluctuation, is alive and healthy and thriving despite its 50-year age. So if T-squared is causing doubts about whether or not temperature works, then the next question is, can you believe abundances in nebulae? Because you need to know the temperature to get the abundances. So how to settle that is an observational problem. There's several things that work here in the planetary nebulae. We know that there's regions where chemical inhomogeneities be present. The white dwarf can throw off material that's very metal rich, very little hydrogen on a white dwarf. And then it can hit the surrounding nebula, which may be the outer layers of the asymptotic giant branch star and AGB star. So they would be different compositions, and there's strong observational evidence that there are chemical inhomogeneities in nebulae. That should not be the case in H2 regions. So the interstellar medium is thought to be chemically well mixed. T-squared is measured to be smaller in H2 regions, but it's still order of magnitude larger than you would predict from the plasma physics. So this has been alive and well, and is the T-squared problem is thriving. What's needed here is to settle this, understand what's going on here. What I would propose is what's needed is a clean room test where several completely independent groups measure the required lines to measure T-squared with different facilities for a sample of H2 regions with no known measurement. So it's important that you not know what the answer is supposed to be before you do this, because there's a positivity bias. If you know what the answer is supposed to be, if you get that answer, you stop checking. If you don't get that answer, you check again and may find out what's wrong until you get that answer. So what happens? So that's this temperature concept, and the question whether there is a temperature is the essential difficulty in getting abundances. There are some questions, and the T-squared problem is the big question. This is an observational question in many ways. Theoretically, the plasma physics has been giving the same answer for a very long time, that T-squared should be close to zero. Observationally, it doesn't seem to be. And this is something that we really need to understand if you want to take care of understanding abundances. Okay, thank you very much.
Thank you, Gary. Very nice overview of the problematics that we have in measuring chemical abundances in nebulae, indeed. Well, first, I didn't know that the origin of the name of your code comes from the sky in Cambridge. So in your honor, I took a picture from my window. For people that don't know, I'm in Cambridge. And so, which demonstrates that it's indeed cloudy during, as we speak.
Well, I have to tell you about this. See, the Willie Fowler connection with Cambridge was still going on, although Fred Hoyle had left when I got there. He still came back. And so there was still this strong connection to Pasadena. And these Caltech postdocs would come to Cambridge, and they would be constantly complaining about the clouds. They said, well, I can't see any mountains. There's no mountains. It's just cloudy. And then I had the office in what's now called the Hoyle building, right next to Martin's, and it looked out into a beautiful pasture with sheep grazing. I thought it was the most beautiful thing I'd ever seen. And so the name comes from a protest against the Caltech postdocs.
All right.
I thought the clouds were great.
All right. So I think we have a few questions. Ranjan Kumar, maybe you posted the question on the chat, but maybe you want to, yes, ask, unmute yourself and ask directly.
Hi, that's an excellent talk. Thank you for the talk. So basically, I have two queries. The first one is how physical is geometrical or plane parallel consideration while doing the cloudy models? And the second one is, how do you tackle the thin approximation of the gas? And I'm asking this in terms of while doing the cloudy models in quasar absorption lines.
There's two answers. In emission lines, if you look at this planetary nebula, the emission is proportional to the square of the density. So what you tend to see is the brightest, densest regions. A telescope is a linear detector. Then so you tend to see the brightest regions. As far as the rate of transfer in the continuum, there are concerns about many things, how to put together a geometry. The approach I've taken is to try to get the plasma physics right. That's a very deep, challenging problem. So what cloudy does not compromise on the atomic and plasma physics. And so maybe the code is halfway done. There's a lot more to go. So that's a deep problem. Get the atomic physics right, get the plasma physics right. What has happened is others have used cloudy as a wrapper on other codes that would put together extremely complex geometry. Which comes to mind now is Christophe Morrissey's Pi Cloudy, and there's others as well. So what those codes do is put together pieces of cloudy models, create a very complex geometry.
Right.
Right. So that's one approach.
So, but basically, can I ask a follow-up question, if that's okay?
Yeah, sure.
Okay, so basically, suppose you have a sightline where, I mean, you won't be able to know, right, what is the geometry of the observer in your sightline. But what if your sightline passes through half of the cross section of the gas, right? In that case, whatever geometry you will assume, that won't be able to give you the correct density or metallicity that you measure, right? So in that case, what should one do, to model the observer?
Well, what we did, I haven't worked on that problem personally, but my job at Cambridge was to work on quasar emission lines. And it became very clear, we can't see what's going on in the center of a quasar. There's a huge range of things going on down there. And there's two assumptions, there's two limits that are actually very simple. One is a plane parallel constant density, single density cloud, one distance away from the star. But the other limit, which is as simple, is it's so complex that you just do an ensemble of clouds with a distribution function. So that's how most quasar emission line models are done now. So you assume some kind of distribution. You would assume that there's a range of densities, and often it become a power law in the density. The number of clouds is density to some power, and they're located at a certain range of radius. And then you can just integrate over that distribution, which is very simple, especially with today's computers. Just create a grid of models, integrate over those, and then you get a result. Now you've gotten rid of some of the complexity. You have a lot of clouds, but then you've introduced a few new free parameters, which is going to be the index on the power laws that are involved. So, one way to think of it, if it becomes sufficiently complex, it becomes simple again, that you just take an ensemble.
Right. Okay.
And thank you.
Thank you.
Unless, I don't know if there are more questions, because we are running short of time. If not, I think we have to, we thank Gary and for the fantastic review. And we move to the next speaker, who is Cesar Esteban. And who is Cesar? Can you start sharing your presentation?
Yes, of course.
And who is going to talk about the precise determination of various chemical elements and the radial abundance gradients in the Milky Way. So if you're ready, you can start. And as usual, I'll give you the 5 minutes warning. Thank you.
Okay, thank you very much. Thank you for the organizers, Oli, Angela, Katarina, and all the organizers for face again to organize another time for the third time this meeting, and also to deal with the complication of the present situation in the world. Well, good morning, afternoon, or whatever for everybody. In the second workshop of this series of meetings, I presented some preliminary results of this project. This project is